In this video, we're just going to continue with our applications involving exponential functions. In our first question, an antique vase was purchased in 2000 for $8,000. If the vase appreciates in value by 6% per year, what is the estimated value in the year 2040? Appreciates means that the value of the vase is going up, so this is an exponential growth. So we can start off by making a table of values to organize our information. Our independent variable is time, but we're not going to put the year 2000 and 2001 and 2002. Instead, we're going to count our years from the year 2000 because this is when it is purchased. So our independent variable is the number of years since 2000. And our dependent variable is going to be the value of the vase in dollars. So year 0 would be the year 2000, year 1 would be 2001, year 2 would be 2002, and year 3 would be 2003. And in year 0, when the vase is purchased, this is $8,000. In year 1, this is $8,000, and we would be taking our price and not just multiplying it by 0.06 for the 6%, we would be including our $8,000. So we would be multiplying by 1.06. And in year 2, we would be taking that $8,000, multiplying it by 1.06 twice. And in year 3, we're taking the $8,000 and multiplying it by 1.06 3 times. So if you're already comfortable with this, you don't necessarily need to make the table of values, but you can if it helps you just organize the information. So let's start with writing our equation. So if we let v represent the value, our equation will be 8,000 multiplied by 1.06 to the power of, and we can use n as our exponent. And don't forget that we need to introduce our variable. So v represents the value of the vase, and n is going to represent the number of years, but since the year 2000. So the question asks us, what is the estimated value in the year 2040? So in the year 2040, how many years is that since the year 2000? Well, that's 40 years, so that means n is equal to 40. So when we plug that into our equation, we need to replace n, our exponent, with 40. And when you do that calculation, you should get that the value of the vase is equal to $82,285.74. So here's our next problem. A 2017 Honda Civic depreciates by 15% per year. If the car was purchased for $18,000, find the value of the car in 3 years. So since the value of the car is going to depreciate every year, that means this is an exponential decay problem. So let's actually try this without even making a table of values this time. We need to state our variables, and we know that v, we're finding the value of the car, so v can represent the value of the car. And n is going to represent the number of years, but since we're starting at 2017, it's going to represent the number of years since 2017. So we know in our equation that we're going to have v is equal to our original price that it started with, so 18,000. And we're going to need to multiply it by something here. So let's look at our question. We know that the Honda Civic depreciates by 15% per year. So what are we going to multiply by? We're not going to multiply by 15%. We know that the car, when it's purchased, is at 100%, and every year we need to take away 15%. So we're subtracting 15% from 100. and that's just 85%. So every year, the value of the car is going to be 85% of the previous year's value. So we're multiplying by 0.85. That's our decaying factor here. And n is our exponent. That's the number of years since 2017. So we know we need to find the value of the car in 3 years. So that means n is just going to be equal to 3. So we can plug that into our equation right away. So we have 18,000 multiplied by 0.85 to the power of 3. So when we calculate that, we should get the value of the car is $11,054.25. In the next problem, a certain type of bacteria doubles every 20 minutes. If the original size of the culture is 30, how many bacteria are there in 3 hours? So let's actually make a table for this one. Our independent variable here is going to be time, and from the question, it's in minutes. And then our dependent variable is the number of the bacteria. So since we know that the bacteria doubles every 20 minutes, we're going to use our time and go up by 20. So we'll start off with 0 minutes, and then 20, 40, 60. And then we also know that the original size of the culture is 30, so that's the number of bacteria in 0 minutes. Then this is going to double, so we're going to take that 30 and multiply it by 2 only once. And then in 40 minutes, we're going to take that 30, multiply it by 2 twice. And then in 60 minutes, we're taking that 30, multiplying it by 2 3 times. So this one's a little different because if you notice that our independent variable, our x values, they don't match our exponents as they have in the past when we've done a table of values. So we need to find out a relationship between these independent variables and our exponent. And our original would also just be 2 to the power of 0. So if we have the exponent 1 here, how can we use 20 to get 1? Well, we can take 20 and divide by another 20 because we know that 20 divided by 20 is equal to 1. Now, can we do the same thing with this 40? If we took our 40, those are our minutes, and divide that by 20, do we get 2? Well, we do, and let's try again. If we took our amount of minutes, 60, divided that by 20, we would also get 3. So there's a pattern here. If we took the number of minutes, divided it by 20, we would get our exponent. So that's very important. That's the relationship we're going to use when we write out our equation. So before we write out our equation, we're going to establish some variables. We can let B represent the total number of bacteria. And we can let M represent the number of minutes that has passed. And let's write out our equation. So B is equal to 30, our starting number of bacteria, multiplied by 2 because it doubles. And our exponent here is not going to be just M because if we go back to our table, we took our number of minutes and divided it by 20. So our exponent is going to be M, our minutes, divided by 20. So now that we have our equation, let's look at what the question is actually asking us. It's asking us how many bacteria there are in 3 hours. So if we have 3 hours, we can multiply this by 60 because there are 60 minutes in each hour, and we're going to get 180 minutes. So then going back to our equation, we're going to have B is equal to 30 multiplied by 2 to the power of 180 divided by 20. And 180 divided by 20 is just 9, so our exponent is 9. So when we actually do that calculation, we're going to get that we have 1,000 or 15,360 bacteria. In the second part of the question, it says, if uncontrolled, approximately how long would it take to get to 3 million? So this time we are given the number of bacteria, and we need to find out how long it would take. We need to find out the number of minutes. So we're going to use our equation, B equals 30 times 2 to the power of m equals 20, and we know that the bacteria, B, is 3 million. So now we can start solving and isolating for m. So we'll need to divide by 30. So we're going to get 100,000 is equal to 2 to the power of m divided by 20. Now so far we've only learned to solve exponential equations by getting to the same base. So we need to get a base of 2, and we need to do this by guess and check. So you can start playing around with numbers. You're not going to get an exact number, but when 2 is raised to approximately 16.6, that's going to be 99,000. So we can just go with that and approximate our answer. So since our bases are the same, this means that our exponents are approximately equal. And then we need to just solve for m here. So we're multiplying by 20 to get that out of our denominator. And when we do that, we'll just get that m is approximately 332. So in approximately 332 minutes, the bacteria will get to 3 million.